Alright, now before the quiz tomorrow, I wanted to go over a couple of examples from the homework assignments and the problems in the back of the book that deal with different spectra, like how to interpret a proton NMR and a carbon-13 NMR, and looking at that data, try to determine what the structure of something is going to be. Alright? So these ones are picked from problems 13.40. And this is the first one that's on there. So this is from 13.40 in your book. And this is what the chemical structure looks like, or not the chemical structure, but the NMR structure. This is all proton NMR. We know what the formula is down here for this compound. Alright? So using the information that I've been given here, what I'm going to do is I'm going to construct sort of puzzle pieces that will allow me to put the structure together and then get a good grasp of what the actual chemical structure is. Now first I'm going to go with the given data that I have. And the given data that I have is that I have C9H12O. Alright? So I've been given a formula, which is great. That's a lot of information for me. Now look at this compound and I do RD, which is the rings and double bonds formula, is equal to 2 times the number of carbons. So I'll put C up here for the number of carbons. This is the number of hydrogens. Oxygen is not included in here. And I do plus 2 divided by 2. Alright? Pretty easy stuff. I do the formula, and what I end up with is 4. And I put a question mark here next to aromatic. I don't know if this is aromatic, but there's a pretty good bet that if it's got a 4, you're going to have an aromatic ring. And there's something in the proton spectra which gives that away. So if I look over here at the proton spectrum, what I've done is I've constructed a table. And this is a great way to organize your data, and it helps organize your thinking. If you can standardize the way you approach these problems, then that's going to help you, especially in a test situation, because you'll have something to fall back on, something that you can look at and say, okay, here's the problem. This is how I'm approaching it. Because this is the way I've approached it in my homework problems. If I keep approaching it in the same standard method, I can solve these problems a lot easier. Okay, so in this case, I've got 7.24. That's the chemical shift, and I've listed all the chemical shifts down the line here that showed up in the spectrum. So here's my spectrum, and I've got about 7.24. Down here, I've got a 4.50. Over here, I've got a 2.38, I've got a 1.75, and down here, I've got a 0.9. And I've listed all of those chemical shifts right here on the side of this data table that I've constructed. I'm also going to list the multiplicity that comes with each one of these peaks and the integration. So that way, all of my information is easily accessible on this table. Okay? So here we go. Chemical shift is 7.24. Immediately my mind thinks, okay, 7.24, it's an aromatic ring. And that's confirmed here by the integration being 5 hydrogens. That's a dead giveaway. You've got a mono-substituted aromatic ring. So what I'm going to do is I'm going to draw and underline the structure of what this means. This is a mono-substituted aromatic ring. The multiplicity here, I wrote multiplet. I don't know what this is over here. Okay, my eyes aren't that good. I can't figure out what that is. But I don't need the multiplicity because I know that that's 5 hydrogens. It's integrated to 5, and I know that it comes in the 7 region. So I don't really need the coupling in this case because I know that that's going to be a mono-substituted aromatic ring. So there's my aromatic ring. Okay, now down here at 4.50, I've got a triplet, and it integrates to 1. So I know that there's 1 hydrogen on there. It's a CH. It's connected to a carbon, and it's a triplet, which means that it's next to something that's got 2 hydrogens. And I'm thinking, because of the lack of atoms that I've got, because I've included 6 carbons up here, I've only got 3 more to make an accounting of. So there's 3 other carbons out there. So I'm going to go with the easiest and most logical suggestion, and that there's a CH2 next to that CH, and that's going to give me a triplet in this case. Okay, so I've got a triplet, 1 hydrogen. So I'm thinking that it's a CH here, okay, a CH that's next to an O that's next to a CH2. Okay, that's what I'm thinking. What else is attached to this thing? Well, if I draw it this way, I've got an H up here and something else that has no hydrogens. So carbon, no hydrogens, is attached in that position. Okay? So now I go down to 2.38. It's a singlet, one hydrogen. If you look at the way this thing looks, see how it's kind of broadened like that? That's a dead giveaway for an alcohol. Okay, so that's the hydrogen and the alcohol, one hydrogen. So boom, that's the OH there. Okay. 1.75 now. At 1.75, I've got this weird multiplet, and they've actually blown it up for you. So you can see this weird multiplet that's here. My God, I don't think I'd ever be able to figure that out. Okay, it's a non-first order system. You look at that and you say, my goodness, that looks like a mess. Okay, and that's often the case. So rather than trying to bang your head against the wall and figure out just how complicated the structure is, don't do it. Okay, the reason being is just it's a multiplet. Okay, and I'll just say multiplet, and I know it's two hydrogens. Some other piece of information is going to be useful to help me resolve this. So I know there's a CH2 here. It's some sort of weird multiplet, so I know that there's something with H's on one side, there's probably something with H's on the other. I also write over here that it's near oxygen. And I write over there that it's near oxygen because it shows up at 1.75. Normally these things don't show up this high, so I'm guessing that it's 1 or 2 carbons removed from the oxygen, probably 1 carbon removed from the oxygen. Now down here, 0.9. You see 0.9, and I want you all to start thinking methyl group, because that's the only thing that shows up down there. 0.9 methyl group. 3 hydrogens, methyl group. All right? So say it to your computer right now. Say it. 0.9 methyl group. 3 hydrogens, methyl group. Computer, why aren't you listening to me? Okay, I could hear you. Even though this is a recording, I could hear you shout that at your computer. All right, so 0.9, 3 hydrogens, and it's a triplet. Okay, this is common. You see that it's a CH3. I underline what I'm talking about. CH3 here, and it's next to a CH2. Okay, the CH2 is putting that into a triplet. And there's nothing else down in this region. Okay, so now I'm going to put my puzzle pieces together. I know I've got an aromatic ring, so I'm going to draw an aromatic ring right here. Okay, what do I know that's attached to the aromatic ring? That's the million-dollar question. And I know it because I've got a carbon here with no hydrogens on it. That's the key right there. The carbon with no hydrogens is going to be this carbon right here because it's got no hydrogens. Okay? And that's why this thing shows up at 4.5. It's not only in the fact that it's got an oxygen attached to it, but it's also got an aromatic ring attached to it. So this thing is really being shifted downfield. And I've got written over here CH2 because I know this is a triplet, so I'm going to write CH2 over here. I know that there's one oxygen, so there's no other oxygen that this could be. So I know that this OH is represented by that signal. All right. Now the CH2 is connected to a CH3. How do I know that? I didn't know it was over here, but I've run out of things to connect it to. I've got 6 carbons here, and I've got 3 carbons over there. That's 9 carbons. Okay, so I'm limited with what else that thing could be. So I know there's a CH3, and I know there's an H over here. Okay, so, well, let me scoot this up a little bit. So this is what I know my structure to be. Now there's a good question that you should be asking is, well, Dr. Wayne, I've got 1 hydrogen here, 1 hydrogen here. Why isn't this a quintet? And that's a very good question to ask, and I hope you're thinking that. Okay? And the reason being is this particular carbon. What's special about that? The special thing about this carbon is that it's chiral. So that there's 2 forms here. There's an R form and there's an S form. Depending upon whether it's R or S, it's splitting the signal differently. So instead of a quintet, what I end up getting is a weird looking mess that looks like this. And it's because I've got that chiral hydrogen. Now this is a racemic mixture, so it's got equal amounts of RS, I'm hoping, and that's what's giving this really complex splitting pattern up here. Okay, things that you could see.